Okay, hello everyone, welcome to this video. This is Analysing Ethernet LAN Switching Part 1. I really apologise everyone that this video has not come out on time when it was scheduled for, so I really apologise for that. And there are some other videos that also have been delayed, unfortunately. So I'm working as hard as I can to get those out as soon as possible for you guys. But nevertheless, I'm really excited about this video. So if we get into the video, what we're going to actually be covering in this lesson, well, firstly, so just checking that this is actually recording. So I've had some issues recording this, and that's kind of okay. I think just making sure everything's okay. Great. So apologize there. What we're going to be covering, well, there's 3 jobs of a switch that we need to know about, okay? And I've got a little acronym that hopefully can help you guys memorize this very easily. We'll be looking at the Ethernet frame format, an introduction to spanning tree protocol. The spanning tree protocol is huge, it's just huge, but so we can't cover so much in this lesson, but the main principle is here just to understand what is actually spanning tree's job, what it's all about. So don't worry guys if you not have any familiarity with spanning tree protocol, you've learned about spanning tree protocol. The point of this lesson is not to go into all the different implementations of spanning tree. That's not what we're learning about here. It's just about understanding what essentially is spanning tree trying to do. What is its role in our network? What role does it play? It's like how we got so many different protocols, but what role does spanning tree play? That's what we're learning about here. Switching logic. So switching logic includes these factors here. So forwarding known unicast frames, learning MAC addresses, and flooding unknown unicast frames and broadcast frames. So these are all aspects of switching logic, so we'll be looking at them as well. So firstly, let's have a look at what the main jobs of a switch are. So firstly, forwarding or filtering. So this F here can actually stand for filtering as well. But forwarding or filtering, that is actually the main role of a switch, is to make that decision, right? A decision of, hey, for example, here's a switch, you know, it receives a frame, okay? It receives a frame comes in, and that switch needs to make the decision of where to forward it. So for example, let's say we have here 3 computers, okay? We've got three end devices. That switch needs to make a decision on where to forward that frame to, and what does it base it on? It bases it on the destination MAC address, which is in that frame. So that's what the switch is doing primarily. Also, learning the source MAC address of each frame received by a switch, okay? Because there's going to be some frames where it's not familiar with the source MAC address. It's like, hey, I don't know you, but you know what? I like you. All right, it doesn't say that, but what it says is, I don't know you, but I'll add your MAC address into my table. It's like if you go to a party and you meet a friend, right? And you meet, you know, you've already got that friend's phone number in your phone. There's no need for you to say, oh, hey, John, let's exchange phone numbers, even though I already got your phone number in my phone. You know, no one does that. But if you meet someone that you never met before, and you like them, and you know, you want to, you know, keep in touch, what do? You exchange phone numbers. And so here's the switch, like, well, let's keep in touch, and let's keep in touch. Let's I'll take your source MAC address, put in my MAC address table. So the switch has a MAC address table, and so with this MAC address table, the switch can now record that new MAC address in its MAC address table. Okay, so the MAC address is then basically saved in the MAC table for future. So he knows in future, is familiar with that MAC address, and he knows where to forward it to, which end device to forward that frame to, if it's got a destination MAC address of that source MAC address at that time. Okay. Lastly is blocking. Now blocking, this is where spanning tree protocol comes into it. So essentially, the spanning tree is there to block redundant paths. We can have loops in our network otherwise, So spanning tree is very, very important there for blocking those redundant paths. Don't worry, we'll be getting more into that. So let's look at the IEEE 822.3 frame format. Okay, so all our frames follow a certain structure, and it's important to be familiar with that structure. When it as network engineers, aspiring network engineers, we should have familiarity with this. So firstly, the preamble. The preamble, okay, that is what starts, and that is basically is signaling that a frame is oncoming, a frame is coming. Okay, so his job there is to basically say, hey, a frame is about to come, brace yourselves. Okay, then the start frame delimiter is the demarcation of, hey, this is the frame, the actual frame now starting. Okay, so this is 7 bytes. Okay, that's what you have there, 7 bytes. Start frame delimiter. Okay, so the actual demarcation of, hey, a frame is starting here. Then we have the destination MAC address, and then followed by the source MAC address, followed by the, okay, so those are pretty self-explanatory, this okay, and then we have the type field. Okay, and this will normally be IPv4 or IPv6, and then we have the data and the padding. Okay, that's what means, padding. So our data is the actual message that's being sent, and then the padding is what's there to, if there's any unused space, it will fill that unused space. So the padding is there. For example, we've got the data here, but we've still got some unused space. So then the padding's job there to make sure that space is being filled. And then finally, the frame check sequence, which is used for error checking. So that is your frame format structure there. Okay, so the preamble is 7 bytes, start frame delimiter 1 byte, and then it goes on, so on and so forth. Okay, so that is our frame format there. Now let's move on. We've got quite a bit to cover. We need to remember this, guys. The structure can be a bit hard to remember. So what I've done here is try to make an acronym, and just like if you remember when you probably learned about the OSI model, you probably read about, please do not throw the sausage pizza away. I'm sure you probably heard of this. The sausage pizza away. Now, I think that's a really good way of remembering the OSI model, the different layers. And also what I try to do is try and create something similar here. But if that doesn't work for you, fine. Try and make something that you will remember, and hopefully that will help you remember the structure. Might not necessarily help you remember what each part does, but at least you know the structure, the order, and from there you can even build on that, and maybe then you can also remember some of the functions of what each does. So that's something I've made, but if that doesn't help you, that's fine. Just try and see if you can make one of your own. Okay, so please send down some trifle, delicious and plentiful, for the children singing. Okay, hopefully it works for you, but if it doesn't, please try and make it own. That's absolutely fine, and I encourage that, because I think it's important to make important for us to, as learners, to make things that work for ourselves, and not necessarily just take everything that someone else is giving, but making those capitalizing on unique learning methods, and making things that help us, that are personalized for us to learn better. So I very much encourage that. Spanning tree protocol now. Okay, so spanning tree protocol is our savior from loops in our network. In one sentence, is stopping those layer 2 loops from occurring to this network. Like you see this frame here, it's just going on and on in a cycle. This was can happen without spanning tree. Spanning tree protocol plays such an important role in pulling our ports into blocking or forwarding states, and this really saves us. There's also a listening and learning state in the original implementation, where there's 4 states in the original implementation, and we go through each one of them, and then rapid spanning tree, which later came out. I don't want to make this too much about spanning tree, that's not the point, but rapid spanning tree basically goes directly from blocking to forwarding state. It basically reduced the amount of time to do something called convergence, which is going through the different states. There were 4 states in the original implementation. Okay, so rapid spanning tree very much improved the time for convergence. So it's a faster version of spanning tree protocol. But both, it doesn't matter which implementation we're talking about here, rapid spanning tree, Pavilion spanning tree, essentially their job is to block those, to stop those loops. So that's essentially what spanning tree is doing. Don't worry, we'll be having more lessons on spanning tree in the future. Now, switching logic, okay? Switching logic, there's different rules, there's different behaviors of a switch, and it's important to be familiar with these. So firstly, if a switch is receiving a frame from a device and it doesn't know that MAC address, not familiar with that MAC address, like I was saying earlier, just like you're a friend at this party and you meet someone you never met before, but you want to take the phone number, you want to exchange details, you can exchange the phone number, you can take the phone number, add it into your phone book, into your phone book, in your phone. And similarly, a device, if a switch receives a frame from a host, a device that it's not familiar with, a MAC address that it has a MAC address it's not familiar with, it can add that, can save that in its MAC address table, add the source MAC address of that frame from the sender of that, which is this from the source MAC address, the sender, it can add that into the MAC address table, so it's familiar in future, and it can make forwarding decisions. So that's the first thing, the first piece of the first aspect of the switching logic I wanted to talk about. Secondly, if a switch is receiving a frame from a known unicast MAC address, it's very easy then. You know, hey, I already know you, and I will, I'm just going to send out that frame because I know which port relates to that MAC address. Okay, it's like you have friends, and you have if you have a friend and you it's like, for example, the destination MAC address, is that links to a certain port, just like if your friend's address links to a certain house, and you need to know the address to know where to, if you have a letter and you need to give it to a friend, you need to have the address to be able to know where you need to go to give that letter. So it's a very easy decision then when we have a known unicast MAC address. For an unknown MAC addresses, okay, the switch can't find out where that MAC address belongs to, which end device. Then the switch sends, what does it do? It sends it to everyone. It broadcasts it except for the arrival port. So that frame is sent out all ports except for the arrival port. And switches, they will forward broadcast frames, multicast frames if no optimizations for multicast are enabled, and also unicast frames as well, if the destination's unknown. Now, MAC addresses, they have quite a few names, so it's very important to just be familiar with these so we don't get confused. So firstly, content address memory table, switching table, also bridging table. So it has quite a few names. MAC addresses themselves have quite a few names: burnt-in address, hardware address, physical address. It's important just to be familiar with those terms. So just wanted to note that there. So yes, if a switch receives an unknown unicast frame, what does it do? It floods it, meaning sending outside all ports except for the incoming port. Now, another note, Catalyst switches name the type of interface based on the fastest speed that interface can do. So 10 out of 100, that interface is referred to as fast Ethernet. Now, I cannot emphasize what's about to come enough, right? And this is MAC addresses and their aging timers. So MAC addresses have an aging timer by default 300 seconds, 5 minutes. Now, if we exceed that, then that MAC address is cleared out. It's cleared out. However, I think a point of confusion, especially in exams, is you might be given a question and it's saying, look, this is a screenshot of a MAC table. And you can see, for example, there's 5 MAC addresses there. And it's it's asking you out of 4 statements which one is the true one. And so you look at the table and you can see 5 entries. And one of the statements is that this switch has learned only 5 MAC addresses. Has learned 5 MAC addresses since it's last been powered on. Now, we cannot say for definite if that is true or not, because there could have been more MAC addresses, but they've just been cleared out over time, over 5 minutes. Excuse me, there. Sorry, my phone's ringing. So it's been cleared out in the last five. It's been cleared out because of the aging timer. So there could have been a lot more, but we only see 5 because that's the 5 that are being regularly used in the last 5 minutes. The rest have been cleared out. So this is something that can be a point of confusion and and I think a real trap. If we don't remember this in the exam, we can easily lose marks in questions. So it's important to remember aging time is by default 5 minutes, 300 seconds, and that means MAC addresses can be cleared out regularly. And so we don't necessarily see everything that's been in that MAC address historically, just by looking at MAC table. It's very, very important. Now, yeah, so this can be a bit of pitfall in the exam if we slip over and we are not, if we're not clear on this. Now, de-encapsulation, re-encapsulation, something also very important to know about. So frames, right, our frames, okay, our frames are being changed at every point in this delivery of this IP header. Our IP header is first, encapsulated by this. Our IP header is encapsulated inside of this frame. When it gets to this router 1 will extract the IP header. It will throw this frame header into the trash, and it will put a new one on. Why? Because the MAC addresses are changing. The source and the delivery MAC address are now changing. Router 1 is the sender, host 2 is the recipient. Okay. So that is thrown into the trash there. Now, once it actually gets to its destination, that IP header is thrown into the trash as well, and we get a new IP header created for this for this return leg now. So, and the frame header is also thrown in the trash. A new one is created. Now, when we get back to router 1, the IP header stays, but the frame header is also thrown into the trash again. This one is thrown into the trash, and we re-encapsulate a new one. So there's constant cycle of de-encapsulation, re-encapsulation here. It has to happen because the MAC addresses, the source and destination MAC addresses are changing. Also, the protocol that is being used, the actual protocol. For example, you got point-to-point protocol, you got HDLC as well. Because these protocols that are being used in transit could be changing, so we need to change the frames accordingly as well. So that's very, very important. And yeah, this just is a note of what I've just spoke about. So the layer 2 technologies might have changed. We might be using HDLC at one link and then PPP in the next link. So that necessitates changing the frame, the de-encapsulation, the re-encapsulation process. Enable password, enable secret. Okay, both passwords are used to enter privileged exec mode, but the enabled secret is much more secure. Okay, again, this is the process of de-encapsulation, re-encapsulation. So you can see, for example, that frame header is thrown into the trash, and a new one is created and added. It's encapsulated into. Okay, the IP header gets encapsulated with a new layer 2 frame header. Okay. Now, show MAC address dynamic, very important command there. Show MAC address table in itself is an important command. Show MAC address dynamic gives us just the dynamic MAC addresses, and we can also do more specific searches. For example, if we're looking for a specific MAC address, we can filter down our results like that as well. And there's more ways of filtering down based on the the interface, the VLAN, and like I just said, the MAC address as well. So that brings me to the end of this video. Thank you so much, guys, for watching this video. I really appreciate it. I'll see you in part 2 because there's more to cover. So thank you so much for watching, guys. I'll see you in the next video. Thank you. Bye.